Hey guys, welcome back to Pop 'em Up Chem. In this video, we're going to be carrying on Unit 4, bonding, and we're going to continue looking at covalent structures particularly, and the molecular shapes that these structures form. But as always, we're going to start with a question. So have a go at drawing the structure of BRF5, pause the video and have a go. Okay, so when drawing BRF5, we're going to follow those steps that we outlined in the previous video. We're going to count up all of the electrons in the molecule, which is 42, gives us 21 pairs of electrons. Bromine is less electronegative than fluorine, so we put bromine in the middle and join all of the fluorines to it, which leaves us 16 pairs of electrons that we then place around each of the fluorine atoms around the outside, leaving one remaining, and then we put that one on the central atom, giving us this structure here. So we're going to base our look at covalent structure shapes on valence shell electron pair repulsion theory, or VSEPR theory. And this theory quite simply states that pairs of electrons around a central atom repel each other as much as they possibly can. And fundamentally, this determines the overall shape of the molecule. So in this theory, pairs are known as electron domains, which includes electrons in covalent bonds, whether it's single, double, or triple, they all count as one electron domain in this theory. And it also includes lone pairs of electrons, which also repel other pairs of electrons around a central atom. So this theory is based on the premise that this repulsion is predictable, and because it's predictable, there is a pattern of shapes that a molecule or ion will keep depending on how many bonds a central atom has to the outer atoms. And that is because the repulsive forces are being kept to a minimum by this separation. And that is why we can think of covalent bonds as being a pair of electrons that repel the other covalent bonds, but we can also think about lone pairs in the same way, as they're just electrons, but they're not participating in bonding like those in a covalent bond. And this repulsion pushes the other bonds as far away as possible. The simplest example of this is in a molecule where there is only two areas of electron domains, like in ethine. Here around each carbon, we have a triple bond to one side and we have a single bond to the other side, two electron domains. So repelling each other as far as possible apart, we end up with a 180-degree angle between the two bonds. So let's have a look at an example. Let's take beryllium chloride. Now we know beryllium is an octet violator. It will happily form a reduced octet with 4 electrons. And we're going to draw the Lewis structure just like how we did in the previous video. We count up our electrons and then we draw beryllium as the central. In this case, it's less electronegative. And then we put the lone pairs. Now, when we have 2 electron domains, as we do here in beryllium, we can look and we can see there is 2 bonding pairs and no lone pairs around that central beryllium atom. So it's going to have a linear shape because it only has 2 places to repel. So 180 degrees away from each other is as far as they can go. So how many of these are there? Well, molecules or ions that only possess bonding pairs of electrons, as in they do not have any lone pairs of electrons, fit into a standard set of shapes. And this is because all bonding pair to bonding pair repulsions are equal, so we have a predictable template for the shapes that are formed. Now these are summarized in this table, where we have the number of electron domains, the corresponding name for that number of electron domains, and the bond angles of the molecules that are formed, with an example on the right hand side. So for people only studying SL, you only need to remember electron domains of 2, 3, and 4. That's linear, trigonal planar, and tetrahedral shapes. For HL students, you need to know those, but also for 5 and 6 electron domains, that's trigonal bipyramidal and octahedral shapes. So before we go about drawing each of these, a quick note on drawing shapes in 3 dimensions. If we have a straight line, that's usually what we would say is in the plane of the board, screen, or piece of paper. This kind of darkened wedged line indicates that that bond is coming out of the board, screen, or paper. So bringing a 3rd dimension into the equation, and a dashed line tells us that the bond is going into or towards the paper or screen. So the shape I've drawn here, we have 2 bonds in the plane of the screen and 1 in front and 1 behind, giving 4 total bonds. So using this system and what we covered just before in the table, I'm going to draw out the regular shapes in 3 dimensions with the angles. So firstly, we have linear, that's for 2 electron domains to the central atom. Then we have trigonal planar, which has 3 to the central atom. We then have tetrahedral, which is our first 3D or out of the plane of the screen shape, and that has 4 to the central atom, 1 in front, 1 behind, and 2 in the plane. For trigonal bipyramidal, which is for 5 electron domains, we have above and below, we have in the plane, and then around this kind of equatorial or axial position around the middle, we have 3 positions, 1 in front, 1 behind, and 1 in the plane. And for octahedral, we have 1 above, 1 below in the plane, and then we have 2 going into the plane and 2 coming out of the plane, giving us this octahedral shape. So here we have the regular shapes in 3 dimensions for 2 electron domains, 3 electron domains, 4 electron domains, 5 electron domains, and of course 6 electron domains, both 5 and 6 for HL only. So the angles of each of these, so we have angles in the linear, trigonal, planar, and tetrahedral, we only have 1 angle, and in the trigonal bipyramidal, we actually have 2 different angles, and in the octahedral, we again only have 1 angle. So the angle in linear is 180 degrees. The angle in trigonal planar is 120, tetrahedral is 109.5, and for trigonal bipyramidal, we have 90 degrees between the bonds above and below this middle circle, if you like, and then 120 degrees between each of those. In octahedral, we have 90 degrees between all of the individual bonds, or we could think about it as they're 180 degrees opposite each other, but usually we just think about this in terms of 90 degrees. Okay, so let's try some questions, and do take the time to really have a go at these. So the first question, draw and name the structure for aluminium chloride, AlCl3. Pause the video to have a go at that. Pop 'em up! So, as always, we're going to count up the electrons and draw Lewis structures just like we've done in previous videos, which gives us 12 pairs. We've got aluminium being the least electronegative, so we're going to place that in the middle with 3 bonds to each of the chlorine and fill in the lone pairs. Now, aluminium is a reduced octet violator, so that's all fine. But of course, we want to work out the shape as well. So we're going to count up the number of electron domains, which is 3 bonding pairs and 3 lone pairs. So that's a total of 3 domains overall, which means we're going to have a trigonal planar structure with a 120 degree angle between each, which just so happens to be how I'd already drawn it. Okay, so time for another question. Do the same, but with methane, CH4. Pause the video to have a go at that. Pop 'em up. So as always, we're going to start by drawing a Lewis structure for this And because we've got 4 pairs of electrons, that means we're going to have 4 bonds to the hydrogens. Now we've got 4 bonding domains and 0 non-bonding domains or lone pairs. So we have 4 overall, which gives us a tetrahedral shape. Now, when we're drawing this in 3D, we want to include the forward wedge and the backward dash to indicate the 109.5 degrees repulsion in the 3D structure. Okay, so now turning your hand to phosphorus fluoride, that's PF5. Pause the video to have a go. Pop 'em up. So hopefully we're getting used to the fact that we need to draw the Lewis structures first at this point. So we're going to calculate our number of electrons, which is 40, which gives us 20 pairs to play with. Phosphorus is the least electronegative here, so we're going to have phosphorus surrounded by the 5 fluorines, all joined by a bond, and then our 15 extra lone pairs left over go on the fluorines. So what shape do we have? Well, around the central phosphorus atom, we have 5 bonding domains, and we have 0 non-bonding domains or lone pairs, which gives us a 5 total. So the shape is going to be trigonal bipyramidal. So drawing that structure in 3D, we're going to include the above and below bonds, and then we're going to have into the plane, out of the plane for 2 of the fluorines, and of course 1 last fluorine that's in the plane, giving us 5 overall. Now we have 2 different angles in this, the 90 degrees and the 120 degrees around the middle. Okay, so I've spoken about lone pairs, but we haven't really addressed them directly. So what makes them different and what makes them similar to normal electron domains? Well, lone pairs exist on an atom and they lie a lot closer to the atom than a bonding pair of electrons do. And because this, they slightly increase the repulsive effect, pushing any other electron domains a little bit more than we would expect. Now, my rule of thumb for this is to reduce the angle by 2 degrees. This may not always be accurate, but it's always within specification limits. If we use the example of NH3, it's nitrogen with 3 hydrogens, we see that we're going to have 3 single bonds to the hydrogens and a lone pair left over. Now, this is 4 total electron domains, so it has a basic geometry of tetrahedral, but it has 1 lone pair. And that lone pair causes a slight extra repulsion on the other 3 bonds, slightly reducing the angle from what we'd expect at 109.5 to 107.5. And so we can kind of order the levels of repulsion, with a lone pair repulsion being more than a lone pair to a bonding pair, and the repulsion to a bonding pair being the lowest. So what shapes can we actually make when we include these irregular geometries? So these irregular geometries are formed when there is lone pairs in the molecule, and those lone pairs cause the angle and the shape of the molecule to change from the regular shapes that we've already outlined. So we go from basic geometries to molecular geometries. So I'm going to outline what these shapes look like in the case of each number of electron domains. So for 2 electron domains, we had a linear shape when we have no lone pairs. And of course, there's no shape if we remove one, as we'll just have 2 points. So beginning with trigonal planar, when we have 3, we have 120 degrees and 3 bonding pairs. When we add 1 lone pair, however, we end up with 2 individual bonds and then 1 lone pair, which is an angular shape. Now that angular shape is going to reduce the angle by about 2 degrees, so we're going to have 118 degrees. Looking at 4 electron domains, we obviously start with our tetrahedral, and when that is equidistant, we have 109.5 degrees as the angle between each of the bonds. Now, if we add 1 lone pair, then we end up with a trigonal pyramidal shape. And if we had two lone pairs, then we end up with another type of angular shape, although the angle will be slightly different than the angular from trigonal planar. The trigonal pyramidal structure will have angles of 107.5 and the angular structure will have angles of 105.5, and they are both reduced from the 109.5 that we would expect from the normal tetrahedral structure due to the extra lone pair repulsion. Trigonal bipyramidal is our 5 electron domain structure. So that's when we have the 3 electron domains around the center and then 2 axial above and below. And if we add one lone pair, then we're always going to add that lone pair on one of these 3 equatorial or middle electron domains. And the reason for that is because that reduces the lone pair repulsion. If we put it on top, then we have repulsion at 90 degrees to all of the equatorial electron domains, whereas if we put it on one of the equatorial ones, then we only have 90-degree repulsion in 2 positions, thus reducing the overall repulsion, which again is the name of the game in VSEPR theory. We call that structure a seesaw structure. If we add 2 lone pairs, then we end up with a T shape, in which we replace 2 of the equatorial electron domains with lone pairs, giving us a T shape. So we had 90 degrees and 120. That goes down to 118 and 88 in the seesaw structure, and then that goes down to 86 degrees in the T-shaped structure. Remember, they are just estimates, but those angles will always keep you within the mark scheme bounds if you're answering questions in an exam. So the last set of irregular shapes we're going to look at is those derived from the octahedral. And remember, octahedral is where we have 6 electron domains, each separated by a 90-degree angle. And we're just going to slowly replace the lone pairs and see what shapes we end up with. Now, if we replace just one lone pair, because all of the angles are equal, that means it doesn't matter which one we show to have replaced with a lone pair. I'm just going to replace the bottom one as we view it here, as I think that illustrates the name best. However, if we have to replace 2 of these electron domains with lone pairs, then it does matter which ones we choose, as we're not going to want adjacent electron domains being replaced by lone pairs. They're going to have to be opposite, because that reduces the amount of lone pair repulsion. Remember, lone pair repulsion being the highest level of repulsion that we have compared to lone pair bonding pair repulsion. In terms of angles, octahedral, we have 90 to begin with. That's going to be reduced by 2 for our square pyramidal, the one with one lone pair, to 88 degrees. And then finally, because we have a lone pair both above and below the plane of the other lone pairs, the angle of the final octahedral, the square planar complex, is actually going to stay at 90 degrees. So let's have a look at a method for us to be able to apply our understanding to be able to determine the molecular geometry using VSEPR theory. So the first thing we need to do is we need to draw the Lewis structure. At this point, we've done a couple of videos where this has been a key skill, so if you're still struggling with that, make sure you get some practice. Then we're going to determine the basic geometry, and remember, we do that by the total bonds to the central atom, where double bonds and triple bonds count as 1, so that's our bonding electron domains, and we add to that the total lone pairs to the central atom. And if we take the total of those two together, then we get the total electron domains that surround the central atom. Once we have the total number of electron domains that surround the central atom, we're able to determine our basic geometry, which we looked at really early on in this video. Once we have the basic geometry, we're then able to determine what molecular geometry is going to be based on the number of lone pairs we have. And you can do this by using the shapes that I just outlined in the video. However, you can also work this out by using the lone pair repulsion rule that tells us that lone pairs will repel each other more than bonding pairs, and therefore the orientation of where the lone pairs will be in a molecule will be determined by that repulsion. So let's go through the whole process with NH4. I'm just going to jump straight in and draw the Lewis structure of NH4, as we should be able to do that by now, even if it takes you a minute or two. So we've done step 1. Then we're going to work out our molecular geometry, and that is going to be the total number of bonding pairs and the total number of lone pairs added together, which equals 4. So our base shape is going to be a tetrahedral one. Now we have no lone pairs in this case, so if we look at the table that I've put here, if we have no lone pairs, then we're just going to have that actual basic shape. So NH4 plus is going to have a tetrahedral orientation and the regular 109.5 degree angles between each of those bonds. If we take NH2 minus, however, we draw the Lewis structure and we see that we've got 2 hydrogens bonded to a nitrogen with 2 lone pairs. So we total up our electron domains, which is the total number of bonding pairs of 2, the total number of lone pairs of 2, which gives us 4. So we have a base shape again of 4, which is tetrahedral. However, now we have 2 lone pairs. So if we look at our table here, when we have 2 lone pairs, those 2 lone pairs are going to repel the 2 other bonding pairs and give us an angular shape. When we have an angular shape, remember we've got 2 lone pairs pushing down the bonding pairs of electrons. This reduces the angle by roughly 4 degrees because we have 2 lone pairs acting on them, giving us a rough angle in this molecule of 105.5. So I'll do one more worked example before we get you doing some questions. So NH3, we have a Lewis structure as drawn on the right hand side, and we've got a total of 4 bonding electron domains and 1 lone pair of electron domains. That once again is a total of 4, giving us a base structure or base geometry of tetrahedral. Now, because we've got tetrahedral but with 1 lone pair, we look at our table and we see that 1 lone pair is going to give us a molecular geometry of trigonal pyramidal, which means we're going to take away 1 of the bonding electron domains, and that lone pair is going to repel the 3 other bonding pairs of electrons and slightly decrease the angle. So the angle we would expect in this molecule goes down by 2 degrees to 107.5. Okay, great stuff. So now you're going to have a go at some questions. So if you get your whiteboards, let's get started with it. First question, state the shape and the bond angles you would expect to find in a water molecule. Pause the video to have a go at that. Pop them up! So after drawing our Lewis structure of water, we can see that we have a total of 4 electron domains, which is going to give us a base structure of tetrahedral, but with 2 lone pairs. That means instead we're going to form an angular structure, and the 2 lone pairs reduce the angle by 2 degrees each, giving us about an angle of 105.5 degrees. Next question, state the shape and bond angles you would expect to find in xenon tetrafluoride. That's XeF4. Pause the video to have a go at that. Pop them up. So the Lewis structure of xenon tetrafluoride is this structure with 6 electron domains. Now we know 6 electron domains in total would give us an octahedral base, but 2 of those are lone pairs. So those lone pairs will be oriented opposite each other to reduce the lone pair repulsion, and therefore give us a square planar complex with a 90-degree angle. Okay, so have a go at doing the same thing, but for the sulfate ion SO4 2-. Pause the video and have a go. Pop them up! So drawing the Lewis structure for the octet violator sulfur, forming an expanded octet here, we see we have 4 electron domains. Don't let the double bonds fool you, with no lone pairs. So we're going to have a basic geometry here. So the geometry a bit easier than you might have initially considered, that is going to be the same as its molecular geometry, which is tetrahedral. And so we can just draw that as we usually would with tetrahedral and our 109.5 bond angle. Okay, last question, and I'll leave you alone. State the shape and bond angles you would expect in BRF5. Pause the video and smash it. Pop them up and pat yourself on the back. So with this structure, we're going to have the 5 fluorines, but we're still going to have one lone pair left on the central bromine atom, which gives us 5 bonding domains and 1 lone pair. This gives us a basic geometry of octahedral, but of course with that 1 lone pair, we're going to have a molecular geometry where one of those electron domains is replaced by a lone pair, and that is going to give us a square-based pyramid structure, of which the angles will be slightly reduced from the regular 90 degrees by the extra repulsion given from the lone pair, which we would expect to be about 88 degrees. So no practical to go with this one, but we do have some questions to complete. Thanks again for joining me, guys. Don't forget to like, subscribe, hit the bell icon, and as always, practice makes slightly better.